In this lesson, we're going to focus our attention on exploring the activation record and stack conventions as it relates to our instruction set architecture. And so you will previously recall that we have a variety of registers that we have available for key components of our applications. And so these registers include our S registers, which represent our caller registers. We have our temporary registers. We have parameter passing registers. We have a register that is used for return values. RA is used for the return address. AT is used for our target address. And SP is used in order to represent our stack pointer. And so now let's talk a little bit about the activation record. And so why exactly do we need a activation record? This is also referred to as a stack frame. And this is beneficial in that the problem that we have is that we need to be able to store appropriate values needed by our procedures. And so these values are, of course, the arguments, the return address, and return values. And so the activation record allows for a space that can be used by the caller and the callee during the execution of a procedure call. And so this is a benefit because it allows for us to avoid appropriate limitations on the number of arguments, the number of local variables, as well as the number of return addresses and return values that we're able to store. To overcome any limitations that might arise, we'll make use of a block of storage for each active procedure call. And this is what we'll refer to as the activation record. And so an activation record is important because it allows for us to statically allocate appropriate blocks of storage for particular procedural calls. And so this will enable us to have many active calls that the procedure can execute at points during execution. And so in order to overcome this, we will need a way to dynamically allocate storage for our activation records when the procedure is called. And this will allow for us to reclaim when the procedure is returned. And so this is best represented using the stack. And so, of course, we have appropriate stack conventions that are in place and that we are able to decrement the stack pointer, and then we can push it. We can pop, which allows for us to increment. And we have our stack pointer that points to the last item placed in it. And of course, initially our stack is going to be empty and it will go from the top of the stack of the low address to the high address. And so let's work through an example to illustrate how we make use of the stack or activation record with regards to our stack pointer. And so at first, we're going to make sure that with our stack, the first step is that we're going to need to have the caller save its appropriate registers on the stack. And so this means if it needs a value in them upon return, we're able to receive it. So here we have our T registers that are saved. And so we have our stack pointer that is pointing to the address for the T registers. Next, our caller would need to place appropriate parameters into our A registers for A0 to A2. And so this allows for the stack to be used for storing additional parameters as needed. And so from our caller function, the additional parameters are stored and our stack pointer is incremented. Next, we'll have our caller allocate appropriate space for any additional return values on the stack. So these return values are added to the stack and the stack pointer is incremented. Once we have the additional return values on our stack, we'll need to advance to the next step. And in this next step, our caller needs to save the previous return address. And so this is saved in our RA register. And so therefore our stack pointer is now incremented and it will point to the previous return address. And so why exactly is this needed? So next, what we'll need to do is we'll need to save, the callee will save appropriate information and registers S0 to S2. And this is what is used during the initial call, from the callee, and this will implement our stack pointer. The callee will need to then allocate appropriate space for variables on the stack. And therefore our stack pointer is incremented and now points to the location of where the local variables are being stored. And so before the return, the callee needs to restore any saved values from S0 to S2 from the stack. And so in this case, it results to our stack pointer being decremented. As things continue, our caller then needs to restore the previous return address, which results in our stack pointer being decremented again. And next, we'll need to return additional values to RA. And so once the callee executes to jump back to RA, the caller will restore the previous return address, and then this will decrement our stack. The caller then stores additional return values that are required. Upon return, the caller will then move the stack pointer to discard any additional parameters. Since we are approaching the end of the procedure call, those additional parameters are no longer needed. The next step is that upon the return, our caller will restore the additional registers from the stack. And so now we want to consider where are local variables in a procedure generally stored or allocated. And so we have a number of different options that are available for us to consider. So are the local variables usually allocated on the stack? Are they usually kept in processor registers? Are they usually kept in special hardware? Are they usually allocated in the heap space of the program? Or are they usually allocated in the static global data space of the program? Or none of the above? Well, we can mark out that they are not going to be allocated in the processor registers, right? We can also rule out that they will not be allocated in the static global data space of the program. What are some other things that we can rule out? We know that they will not be allocated in the heap space of the program. And so that leaves us with 3 options. And we know that it won't be none of the above because they have to be stored somewhere. And so we can rule out that they won't be stored in special hardware because that would be too much of a cost for us. And so local variables are going to be stored in a procedure. And so now let's return our attention to better understanding an activation record and how it occurs. So let's say we consider a number of different methods that are nested within one another. We have our main method, which calls foo, which then calls bar, which then calls buzz. So our activation record provides us with an appropriate way to understand how each of the procedures are going to communicate with one another. And so this will be a strong representation between different callers and callees. And so our previous examples were able to demonstrate how each of the callers and callees would process through communicating with one another. And it shows the buildup that occurs by the callers and various callees. And so depending on how the procedure calls are nested, it's important to keep in mind that we can have multiple multiple activation records that are represented on our stack. But it's also important to keep in mind that at any specific point in time, we only have one activation record that is going to pertain to the procedures that are currently being executed. And so in this case, we have an appropriate activation record for our BOS functional call. And so now let's consider, what do we need in order to implement appropriate components for recursion? Would recursion require any additional tools for us to utilize? Not necessarily, because recursion is going to simply represent additional calls being called repeatedly. So these are just multiple procedures that are occurring in a recursive manner, and therefore it is appropriately supported by our activation record. And so this means that we don't need any additional modifications in order to fully support our recursion within our instruction set architecture.